So we've seen that a parameterization of the unit sphere in terms of the spherical coordinates phi and theta leads to unit tangent vectors due to theta, unit tangent vector due to phi, normal vector t theta cross t phi. Now I'm not going to show it here. I'll come back to it after talking a little bit about this in a next video or two. We get this normal vector and it has magnitude that's equal to the magnitude of sine phi. Now that gave me a little bit of trouble. There's something about that didn't seem right to me because I was thinking in terms of rectangular coordinates where your normal vector has constant magnitude. And there's something I didn't like about that, but it's okay. The reason this works, even though sine phi approaches 0 as you approach the z-axis, is that your t theta vector gets very small for points that approach the z-axis because you're at a very small distance from the z-axis, meaning that a small change in theta doesn't give you a very big vector. Okay, now I'm not going to, you don't need to understand that completely, but if you pursue that just a little bit, that is the explanation. Now we have another parameterization that I didn't write down on the board, but now I've written it. R equals xi plus yj plus the square root of 1 minus x squared minus y squared times k. And we should say that x goes from, I want to write 0 to 1, negative 1 to 1, and negative square root of 1 minus y squared less than or equal to x. Sorry, negative square root of 1 minus x squared less than or equal to y less than or equal to the square root of 1 minus x squared. And that's a standard parameterization of the unit sphere in terms of the parameters x and y. Now if we do something very similar to what we did here, where we did t theta cross t phi, we take our tx and ty vectors, which are easy to calculate. The x derivative of this vector is just I. There's no x, the x derivative of y is 0, and the x derivative of this is negative 2x over 2 times the square root of 1 minus x squared minus y squared, which reduces to x over the square root of 1 minus x squared minus y squared. So you can easily verify that for this vector, for this parameterized vector r, which as x and y go through these values, describes the unit sphere. Tx is this, and ty is very easily calculated to be this. And then tx cross ty, again, easily calculated. I cross j gives you k. I cross k gives you negative j, so that we're going to have a negative of your negative y over the square root of 1 minus x squared minus y squared times j. And k cross j gives you negative I, so that you get the negative of the coefficient of k here, x over the square root of 1 minus k squared minus y squared. And if you don't understand what I just said, write this down, and calculate their cross product. If you want to use the determinant thing, you can, but we can really kind of easily do this using the distributive law. And of course, k cross k is 0. Whichever way you calculate it, this is the cross product. And then we can put all this over common denominator. We'd have to have the square root of 1 minus x squared minus y squared k divided by the square root of 1 minus x squared minus y squared to get a k. But clearly, putting this over common denominator, this is easy algebra, gives you this. Then we could also notice that the square root of 1 minus x squared minus y squared is just z. So we could replace that with z, although that's not going to be particularly useful if we're trying to integrate in the parameters x and y. Still, we want to keep in mind that with this parameterization, z is equal to this. Now, I scribbled some stuff down here and realized it was unreadable, so don't even try to read it. I'm going to pick that up in another video or two and address how this gives you the same result as this for the surface area of a sphere. Kind of a neat application. Okay, so right now you see how this parameterization gives you this normal vector, this magnitude of the normal vector, and this parameterization gives you a different magnitude of your normal vector, which just turns out to be 1 over the square root of x squared, 1 minus x squared minus y squared. We'll get that when we come back to this. Okay, now we're going to move on to this idea of the curl and some characteristics of the curl before we return to this.